Okay, so the next one is longitudinal shear in a beam section. Okay, so we are going to analyze the strength of joints okay in shear loading condition. What I like to emphasize over here is the strength of the joints. Okay, so yeah, I'd like to emphasize on that. Okay, so if we have a structure X and Y rotation about Z, and we have a beam, you can have a beam, and the beam, I'll draw a line down here and I'll elaborate what is that all about. Okay, and the beam is overhang, for example, for this case, and then you have loads, okay, in this sort of region. Okay, so you have omega Newton per meter, you have a P, and then in this beam, okay, is made of, I mean, this beam, hear me out first, okay, you have spacing of the nails down here, or rivets, okay, so these are the spacing of rivets, nails, bolts, okay, etc. So now I'm going to draw a cross-sectional view now. Okay, now I'm going to draw a cross-sectional view. So now, if this is my transformation now, so this is my Y, Z, okay, and this is my rotation in my X, right? So now the structure look like this. Wait. Okay, now the structure, and the structure is made of different members now. Okay, it's made of different members now. Right, now your structure look like this. And this has been fastened by, if it's a wooden structure, it will be nails. Okay. So these are the positions positions of the fasteners. Okay. Now, if this beam were to fail, so this beam is not made of a solid T, right? So you have different parts. So this is member number 1, member number 2, member number 3, and member number 4, right? If this part were to fail, Where will it fail? Anyone? If this part were to fail, where is it going to fail?
At the positions of the fasteners?
Yeah, at the joints. Right. So where it will fail here first, or it will fail here, or you'll fail here. Right. So it's like if you are going to go into a battle or a fist fight, I'm not saying that I don't endorse violence, right? But if someone's on the street, he's 2 times your size or 3 times your size or half your age, right? If you have to engage the person, you have no choice. Do not hit him on the chest, okay? It's not going to hurt him. Hit the knees, hit the hips, elbow, attack those positions because the joints are the weakest. Same, okay? Same for structure also. Okay, so to elaborate this, the beam, okay, this beam is made of 4 members, right? And to highlight what I just said, failure were always occurs at the joints, okay? Because it's the what? It's the weakest link, okay? I mean, you will not use a structure that's weaker than your fastener, will you, right? Okay. So the calculation, right? The calculation that we're going to use. Okay, I'll let you guys copy first. So the calculation, the formula that we're going to use. Okay, so to calculate the shear stress, okay, shearing stress or strength of joints. All right. So the formula will be shear flow. Now we are going to have a new formula, but it's not difficult to remember. Okay. So we know that shear flow Q is equal to VQ over I, right? And then if we look at the units, right? This is Newton meter cube over meter 4. This is Newton per meter. Okay. Now this is also related. Okay. This is also related to Q is equal to the force the force that the joints could resist divided by the spacing of the fastener. Okay. And you've seen the spacing of the fastener before is basically this spacing. Okay. So this analysis will help you determine what is the spacing that's required. Okay. So I as some of you know, I have my own consulting business, and sometimes I do calculation for landscaping company. Okay, they are going to build a huge deck. Okay, and on the deck, someone's going to put an outdoor kitchen on the deck. Okay, stones. Okay, knowing the weight. Okay, and then if that's the case at that area, how much joints had to be put, what are the spacing of the nails? Okay, what are the spacing of the nails? Because you have a stove on top, the weight is a constant applied load. Okay, it's some of these stove are like 3 human beings weight into a small area. Okay, so what is this spacing of the bolts that you have to have, or the nails, what are the intervals? Okay, so things like that. So I find this really useful. Okay, so the formula used, as you can see, is shear stress is equal to VQ over I. All right, seen this before. All right, as I told you, this topic is only 2 formulas, and the spacing of the joints that you could resist. Okay, then another formula that we're going to apply is shear stress. Right, shear stress is equal to VQ over IT, and together with this, okay, together with these rules still apply. Okay, that's why I told you these rules are really handy. Okay, you can apply it in the entire textbook chapter, it will still work. Okay, where is my undo? Does it do the same? Yes, stupid thing. Hold on, my bad. Okay, these rules still stand. Okay, we're gonna apply the same rule. Okay, so enough of me yapping. Let's do this problem. Okay, let's do another example. So I think this is our 1, 2, 3. This is our example number 4. Very interesting. Yeah, in this topic, you have to also design your shear flow. Then you can visualize better. Okay, if visualize the failure. If you don't design the shear flow, you cannot visualize where failure will occur. Now, one difficulty of this topic, okay, as you can see, you have failure. You have to know how to do failure analysis is required. Okay, I will elaborate on that later on. Okay, so let's look at one example over here. Where is the example? Yes, let's look at this example. You can still hear me, right?
Yes, sir.
Thank you. I thought I got mute again. Okay. So this is the problem that we're going to look at. A double web girder is constructed from 2 plywood that are secure to the wood member at the top and the bottom. So what you see down here is you have 2 bolts, right? One at the top, one at the bottom. So it's a single bolt that secure both sides. Okay. So what is given is we have our normal stress allowable is set at what 8 times 10 to the power 3. Now, for now, we are going to ignore the normal stress first, okay? Because I've not taught you guys to do bending moment yet, okay? So we're going to ignore the normal stress first, okay? But the shear stress allowable